Hey friends, my name is Rizula Khedekar. Today we are going on a deep dive into some of the most beautiful ideas in quantum physics that are spin, spin operators, expectation values, and variance. As they sound, they are interesting. These aren't just textbook ideas, but they are the building blocks behind quantum computers, MRI scanners, and even our understanding of the quantum world itself. Stick with me because by the end you will have a solid mental map of how all these fit together. So we'll start with spin. Let's start with the basics. What even is spin? In classical physics, we hear spin, we think of objects rotating like a spinning basketball, but in quantum physics, spin isn't actual spinning motion, it is not an actual spinning action that is happening. It's an intrinsic property of particles, just an intrinsic property, not real action, more like an inherent label that defines how they behave under rotations. Think of spin like an internal compass that points in direction, but that direction is not always sharply defined until you measure it. Measurement is really important. Electrons, for instance, have spin of -1/2. When you measure their spin along any axis, say the z-axis, you will only ever get two possible results. That is plus 1/2 into h cross, and we call it spin up. And second, that is -1/2 h cross, we call it spin down. Mathematically, spin up is just a column matrix with two entries, with first entry as 1 and second as 0. And spin down is also a column matrix with first entry 0 and second entry 1. Quantum particles can exist in states that are part up, and it is that are part up and part down. That is called superposition. For example, alpha into spin up plus beta into spin down. The condition is alpha square plus beta square is always equals to 1. Mod of alpha square plus mod of beta square is always equals to 1. So it's not either and or until you measure it. Um, a quick thought through experiment. Imagine asking someone, are you happy or are you sad? And they answer, I'm 60% happy and 40% sad. That's the spirit of quantum superposition. It can be 100 and 0. It can always be 50-52, and it can always be something like 60-40, 60% spin up, 60% spin down. That is what superposition is. Now we'll move to operators. Um, in quantum mechanics, we describe measurements with mathematical tools, and those mathematical tools are called operators. For spin, the main operators are Sx, that which measures the spin along x-axis. Similarly, Sy, which measures the spin along the y-axis, and Sz, that measures the spin along z-axis. These are linked to special matrices, the polymatrices. Polymatrices are 2 by 2 matrices, 2 by 2 matrices, and there are three of them with 0, 1, 1, 0 as first matrices, 0 minus I, 0, the entries of second matrices, 1, 0, 0 minus 1 as the entry of third matrices, as you can see it on the screen. The actual spin operators are Si is equals to h cross by 2 into polymetric matrix of that particular x, y, or z. Key properties are operations are Hermitian, that is real and measurable values. And second is they don't commute. Non-commutation means you can't simultaneously know the spin along x and spin along y precisely. You can know it, but you cannot know it precisely. This ties straight into the uncertainty principle. You must have heard of uncertainty principle, right? It's just the point straight to that. A quick question for you guys. Which pair of operators do you think also do not commute? First option is SY and SZ. Second option is SZ and SX. Did you think of an answer? You're right, most probably. Let's keep it a mystery. Now we'll move to observables and eigenstates. A quick recap for everyone. Observable values are something measurable associated with a Hermitian operator. Eigenstates are the special quantum states where measuring is an observable gives measuring an observable gives a definite result. If a system is an eigenstate of SZ, say spin up, then measuring SZ will always give plus h cross by 2. In contrast, if the system is in superposition state, measurements are probabilistic, which is you cannot tell the measurements precisely. They are probabilistic. It depends on it basically related to probabilities, which is not very certain. So yeah, and a little story like just to get the topic of observable and eigenstates better in a easy language. Imagine flipping a weighed coin. It lands heads 70% and tails 30%. In a quantum state, you can set up weight superpositions like that. But even weirder, the weights can involve complex numbers. Like, yeah, you heard that right. The weights can involve the complex numbers, the numbers which don't exist in real life. Now we will move to expectation value. Expectation value is another very interesting concept that we are going to cover in this video. Expectation values is the average outcome. If you measure a system like really many times, and the formula is shown on the screen. And let's go to the examples directly. Like for example, it is pure spin up along z-axis. So Sz is equals to plus h cross by 2 as we talked earlier in the video and shown earlier. And second example is for equal superposition 1 by root it is 1 by root 2 into spin up plus spin down, and hence we find expectation value of Sz is 0. Um, Also, it is equal superposition. That's the reason we took the 1 by root 2. Um, so, if it would not have been an equal superposition, 1 by root 2 would be replaced with some other values. And we will not go there as it is not in our syllabus. Uh, Meaning, also we find expectation value of Sz equals to 0. Meaning no preferred spin direction along Z. That is pure uncertainty. Uncertainty, guys. Now we will move to variance and quantum uncertainty. So now let's move deeper, okay? Variance tells us how much spread there is in measurement results. So the formula is variance of A is equals to expectation of A square plus expectation of A whole square. If variance equals 0, you are in an eigenstate. Measurements are certain. If variance is not equal to 0, then you guessed it right, measurements vary around the expectation value. Examples are for spin up expectation of Sz is plus h by 2, h cross by 2, and expectation of Sz square is h cross by 2 whole square, and the variance is 0. But for superposition, expectation of Sz is 0, and expectation of Sz square is h cross by 2 whole square. So here the variance is h square h cross by 2 whole square. It's like big variance, big uncertainty. Think about guessing the weather tomorrow. If you live near the equator, the variance is low. That is, it's always hot. It's You get it. We live near the equator. Near the poles, the variance is huge. Now we will move to the real world connection of magnetic fields and spins. Practical examples we will see here. So, some of the practical examples are: put an electron in a magnetic field along the z axis. Its energy depends on spin orientation. If electron is spin up, it's lower energy. This is the working principle behind MRI machine, electron spin resonance experiment, and even quantum computers using spin qubits. Expectation values of spin tell researchers the overall behavior of huge ensembles of atoms, like how MRI scans build pictures from atomic spin. Now we will conclude the video. So it's a wrap up, guys. Thank you so much. Today you learned about spin is intrinsic, not literal spinning like a basketball or something. Operators describe measurements. Expectation values are quantum averages. Variance measures uncertainty. Before you go, a quick question for you all. If a system's variance for SZ is 0, what can you immediately say about the system state? Pause the video to think about the answer. Yes, you guessed it right. It's an eigenstate of SZ. Thank you so much for watching. Bye bye.